Analog multipliers improve the accuracy of high-side current sense measurements. Welcome to this module on analog multipliers improving the accuracy of high-side current sense measurements. This module shows how to use an analog multiplier integrated with a high-side current sense amplifier to measure battery charge and discharge currents in portable equipment and notebook computers. The whole module contains 10 pages and will take about 10 minutes to finish. A high-side current measurement scheme employs a sense resistor connected in series between the voltage source, for example a battery, and the load. A high-side monitor connected directly to the power source, on the other hand, can detect any downstream failure and trigger appropriate corrective action. High-side monitors are also well suited for automotive applications in which the chassis serves as the ground potential. The high-side approach does have a disadvantage. The current sense amplifier must be able to sustain a possible high-voltage common mode input, depending on how high the voltage source is. The high-side scheme is typically designed around current sense amplifiers. In contrast, measurements taken with the low-side scheme employ a sense resistor in series to the ground path. The low-side scheme presents two significant disadvantages not shared by the high-side counterpart. Firstly, in the low-side design, if the load is accidentally shorted to ground, then the current sense amplifier is bypassed and cannot detect the short. Secondly, the low-side scheme introduces an undesirable resistance in the ground path, thus creating a split ground plane. The low-side scheme can be achieved by a simple op-amp as long as it has common mode input with ground sensing capability. The MAX4211 is a high-side current sense amplifier with integrated analog multiplier. This device measures the power delivered to a load, as illustrated in the figure. The power delivered to the load is defined as the product of the load voltage and the load current. The high-side current sensor provides a voltage output proportional to the current in the load. This voltage is fed to the analog multiplier, whose other input directly senses the voltage at the load. The output of the analog multiplier is a voltage proportional to the power of the load. There is another way to use the analog multiplier. Instead of connecting the analog multiplier's external input to the voltage of the load, connect it to the ADC's external reference voltage. In this design, the analog multiplier is not measuring power, but is relating the voltage output of the current sense amplifier to the ADC's reference voltage. The figure shows this application, where the MAX4211 measures the battery charge and discharge currents. The voltage output, P sub out, is fed to a 16-bit ADC with an input voltage range from 0 to V sub ref. Here, V sub ref is provided by an external voltage regulator and should be between 1.2 volts and 3.8 volts. 3.8 volts in this application example. The analog multiplier input accepts a voltage between 0 and 1 volts, so the two resistors, R1 and R2, divide the 3.8 volt reference voltage. Assuming that R2 equals 1 kilo ohm and R1 equals 2.8 kilo ohm, then V sub in equals 1 volt. The MAX4211 has a gain of 25 and a sense voltage range, V sub sense, from 0 to 150 millivolts, which produces an output voltage at both P sub out and I sub out between 0 and 3.75 volts, proportional to the current that flows on the load. The figure shows the same application with an ADC that has an internal voltage reference. There is an advantage to using the P sub out output of the current sense amplifier instead of the I sub out output. The signal fed to the ADC, which is proportional to the current in the load, is scaled by the V sub ref voltage. Note also that using the P sub out output can relax the accuracy requirements demanded by the voltage reference. This relaxed demand on the voltage reference happens because the digital code produced by the ADC depends on the ratio between its input signal and its reference voltage, which represents the full-scale value. The P sub out output is a direct function of the reference voltage. Therefore, the ADC measurement is, in principle, independent of the accuracy of the reference voltage. If the I sub out were connected to the ADC, however, then the ADC would see any errors in the reference voltage as a full-scale error. The two equations shown represent the ratio of ADC input to ADC full scale. Equation 1, which uses the P sub out output, is not dependent on the accuracy of V sub ref. Equation 2, which uses the I sub out output, produces an error that is the inverse function of the V sub ref accuracy. The overall accuracy of the system shown in figures 2 and 3 depends on many factors: resistor tolerance, the amplifier's gain error, voltage offset and bias current, reference voltage accuracy, and ADC errors. The solution presented in these pages uses the analog multiplier of the MAX4211 to improve the system accuracy by eliminating one of the causes of errors, the inaccuracy of the reference voltage. The figure illustrates the second error source listed here. A heavy load is connected to V sub ref and its value drops from 3.8 volts to 1.2 volts when the load is increased. P sub out matches the V sub ref drop profile and changes accordingly. The solution presented in the figure of the previous slide uses the analog multiplier of the MAX4211 to improve the system accuracy by eliminating one of the causes of errors, the inaccuracy of the reference voltage. The integrated analog multiplier of high-side current sense amplifiers is typically used to measure the power at the load. There is, however, another possible application for this integrated multiplier. The current sense amplifier can be connected to an ADC that uses either an internal or an external voltage reference. In both cases, the overall accuracy of the measurement strongly depends on the accuracy of the voltage reference V sub ref. By multiplying the load current measurement with V sub ref, the overall accuracy of the ADC measurement is no longer dependent on voltage reference errors. Using this alternate design, one can improve measurement accuracy even in the presence of a low-cost and less accurate voltage reference. The MAX4210, MAX4211 low-cost, low-power, high-side power current monitors provide an analog output voltage proportional to the power consumed by a load by multiplying load current and source voltage. The MAX4210, MAX4211 measure load current by using a high-side current sense amplifier, making them especially useful in battery-powered systems by not interfering with the ground path of the load. The MAX4210 is a small, simple, 6-pin power monitor, among which the MAX4210A, B, and C integrate an internal 25:1 resistor divider network to reduce component count. The MAX4210D, E, and F use an external resistor divider network for greater design flexibility. The MAX4211 is a full-featured current and power monitor that combines a high-side current sense amplifier, 1.21 volt band gap reference, and 2 comparators with open drain outputs to make detector circuits for overpower, overcurrent, and/or overvoltage conditions. The open drain outputs can be connected to potentials as high as 28 volts, suitable for driving high-side switches for circuit breaker applications.